Hello and welcome to the lecture Diffusion Model Part 2. In this lecture, we start with reverse diffusion. Then we are going to learn the diffusion models via variational inference. Then we try to understand what do you mean by evidence lower bound, that is called ELBO. Then we figure out what is ELBO loss. Then we discuss about model parameterization and noise parameterization, and we conclude our lecture by the algorithms of the training sampling process. In the last lecture, we have seen the forward diffusion, that is the noising process. Now here we see the reverse diffusion, that's been denoising process. The backward diffusion process, that means this denoising, is the generative part of the diffusion model, as we can understand, because now we start from the pure noise, Gaussian noise, and slowly denoising the images so that we can get back the original image. That was just the reverse case of our forward pass or forward process. It learns to reverse the forward noising process, transforming pure Gaussian noise into a structured data. So you can see this from pure Gaussian noise to structured image or structured data. Now in the forward process, this is fixed, not learned. This q of xt given xt minus. Now here you can please try to understand, this is reverse, so this is forward. So xt from xt minus 1, so this from this that we will try to see. This is basically a kind of noise addition, and what mathematically we can write this, that we have seen in our previous slides, because this is a Gaussian noise and this Gaussian noise of this mean and variance. So after many steps, you can say we start from here in forward process, and after many steps we get the kind of pure Gaussian noise. So it is very close to a pure Gaussian noise, zero mean, and this. Now goal of the backward process of denoising is what? That this is the process of from xt. How can we xt1 minus 1? Because it is a xt minus 1, xt minus 1 to xt minus 2, and so on. That is the backward process. So that starting from the noise. So xt is a noise, or you can say this is the xt, and slowly we denoising. So we can say we progressively or successively denoising at each step to get back the original image. So this original image means produce the realistic sample. It is not that when we are doing this we are get back the exact, but some similar. That's why it's a generative image. Okay, so as a whole this is the reverse diffusion process, and that is basically by this process reverse diffusion we can generate samples. Okay, now if we can reverse the above process, that above process means the forward process, forward diffusion process or noising process, and sample from this q xt given xt minus 1. So this will be able to recreate the true sample from the Gaussian noise input, that is this. So if we can sample it, note that if beta t is small enough, this xt given xt minus 1 will also be Gaussian, but this we cannot do, because we cannot easily estimate this q of x, because it needs to use the entire data set, and therefore we need to learn a model p theta. So now this thing we cannot do in straightforward way, so we do it by means of some model. So kind of, you can say, neural net or something that parameterizes with theta and x 0 to t. So because this is the forward direction process, to approximate these conditional probabilities in order to run the reverse diffusion process. So now this, what is this p theta? P theta is a p of xt, and then we can keep on multiplied this p theta xt minus given xt. Okay, so this is the basic understanding. So what is the way we can do it? What is the mathematical formulation of p theta of xt minus 1 given xt? This is basically the reverse diffusion process, that is basically this type of denoising. This is basically what we are doing. We are basically removing the Gaussian noise to get the xt minus 1 from xt. So this mu theta, this is the mean and this is the variance of this. So this is the mathematical formulation of this. Now we have to find how we get it. Now here this is the illustration that how we are going to achieve this. Here you can see, now this is very interesting figure. It is given in the main paper, that this is the forward trajectory. That means t is equal to 0 to t is 2. We keep on adding the noise. But here also we can say it is not the forward. Rather, it is becoming from here we start and we are keep on removing the noise and we get back this. The question is to learn this thing p of x from this two distribution. If we minimize the distance of this distribution, then we can somehow estimate this particular p theta distribution, because what exactly we want to do, we want to learn this, we know this, so the KL divergence between them should be minimized. So somehow we have to minimize this divergence between q of 1 to t x0 and p of theta of 1 to t. So you can understand, I think, from here, this is the forward process, this is the backward process, we get this. So can we, if we reduce the distance between these two distributions, that we can somehow mimicking this p theta x by this q, and that is we can do by this. Now how mathematically it can be done, we will see. Let's see. Now here also the same diagram, I think, just for recall, say this is the reverse direction, from we start from the noise and xt and we keep on denoising, and from xt to xt1 we are basically. So what we are basically doing, since this is unknown, we try to find out this p theta. We are estimating this. From where we are estimating? That we are estimating by minimizing the scale divergence between t to q and p theta, that in this way. Okay, so the Markov chain of forward reverse diffusion process of generating a sample by slowly adding or removing noise, that is basically what. And here we will going to in next few slides that variational lower bound we are going to. So what we at is every step we are doing this. This is just a one step it is. So now we have to understand how we can do this. So the diffusion models can be derived as a special case of latent variables model trained with a variational inference. Now, why this is latent variables models they can use? That this model can be derived a special case of latent variable model trained with variational inference that we'll see just in a few slides. Now treat the entire forward diffusion trajectory as the latent variables. Okay. So why it is so that this forward diffusion trajectory means that everywhere we are keep on adding this noise. So from it is from some noisy version. So what we are basically trying to do, from some latent space we can create the corresponding true images or kind of reconstruct, kind of generate the samples which are very close to the real samples. So from that concept and optimize the variational lower bound ELBO on the data likelihood at every step we are doing. So the latent variable is that will x1 to t. So the joint generative model is basically p theta x not t, that is p of xt. We start from here and we put this multiplicative thing. So p theta xt minus 1 given xt, where this pxt is what? It is a pure Gaussian noise and it is p of theta xt given xt is learned reverse process. So what we have to do? We have to maximize log p theta of x0. So that part. Then we can make a setup where we can get back the image or the data, real data is very close to the real samples. Okay. Now let's see how we can do it. The forward process has the variational distribution. So we start our understanding from this forward process. As we have seen before, this forward process, which is happened to be fixed in this case, that q of x1 up to t given this x0, this is forward because from x0 to xt. So this is with this capital pi, so that is the multiplicative in terms. So this particular thing acts like a variational distribution. Now we have to find out that from this we have to model our p theta. Now here, as we have seen in the previous figure, that in this figure, that such setup is very similar to variational autoencoder, what we have discussed in last lecture. Thus, we can use a variational lower bound, that is ELBO, to optimize the negative log likelihood. So we are basically, this result we have taken from the variational autoencoder. I think you can recall it. That is basically the evidence lower bound or ELBO, that log of p theta x, that is the negative, that's less than is equal to minus log of p theta x0 plus the KL divergence between q and p theta. Now you can see that is very important. This it is x0, that is what that we have to understand here. Here this qxt xt by xt is not known, but this is known. So from here to, if we somehow minimize the distance between these two, then we can get or at least model this. So exactly this is we trying to do here, that you to q and x0 is p theta, that this scale divergences. And since we know that after this kind of some algebraic manipulation, the expectation of log of q of x to t given x0 by p theta x0 x naught to t. So this loss, this variational lower bound, this kind of loss is basically this. This is loss. It is typically get this equal to minus eqx0 log p theta x0. So this is just mathematical derivation or formulation. The basic idea is that by optimizing this bound, it is possible to maximize this p theta x0 and minimize this loss. Exactly what we want to do. Okay, so that we minimize this loss so that we can back when you are doing the reverse process, we can get more realistic samples. Here q is a fixed and we optimize p theta. Okay, now we expanding ELBO. So to convert each term in the equation to be analytically computable, the objective can be further rewritten and combination of several K divergence and entropy terms. So that what we have seen, this is the lower bound of variation, lower bound of this loss. And now we intentionally omit, there is a lot of algebraic manipulation. And after that it can be shown that this thing can be written as this. And there is a three major term. One is prior term, that is expectation of this scaled regions of k of qxt given x0 between and p theta xt, this between these two distributions. And this is a summation of this scale divergence between these two and log of p theta. This is called reconstruction. So the important is that these three components, what is the meaning, what is the basic understanding of these three components? Let us see one by one. So this is the prior term, denoising term and reconstruction term. Now here we can see that this VLB, this lower bound, basically this that we have to understand. In every step we are getting this, and that if we add it, we can get this. So the level each component in the variation lower bound loss separately. So this. Now what is this LT? This is what that we have seen. This LT term, this prior term. That is D of KL. That means the KL divergence between Q and P theta. What is DL small t? That is the KL divergence between this xt given xt plus 1 to x0 and this xt given xt plus 1. Okay, for 1 is equal to 10. So there is so many steps involved here. And L0 is minus log of p theta. It is x0 x1 given x1. So here we are basically from this paper, every KL term in this lower bound, this loss of VLB except L0 compares to Gaussian distribution. Say both they are comparing to Gaussian distribution, and therefore they can be computed in closed form. So these two we can achieve. LT is a constant and can be ignored during training because Q has no learnable parameters. Okay, and XT is a Gaussian noise. So this is the main first author of this main paper in DDPM paper. This Weight al 20 model L0 using a separate discrete decoder derived from this. distribution. Okay, so this is important results. Now we can say this prior loss compares the final xt and is often 0 by construction. This is the loss, the prior loss. The key components of the diffusion loss terms which the key components of the diffusion loss, the terms which measure whether the learned backward process, this PT, so looks like the real backward process. That is very important. That is we actually want to do. That learned process should be very similar to the actual process. So this is the for every step. Okay, and the reconstruction term L0 is the probability that true x0 the best case of x1. That is this loss. So that we can understand these three losses and what are the effect of our system. Okay. Now we understand that these are the losses. Now with this background we have to parameterize our model. Because the forward process is Gaussian, this Q of this is also Gaussian. No, this is Gaussian process, so this must be a Gaussian. Now if we parameterize this p theta, this because this parameterized, this is as a Gaussian sigma square identity, then each k term becomes a simple quadratic loss. So this is where we parameterize the model. Okay, so given this setup. Now the diffusion loss term that we have seen here, that the diffusion loss term is this d of k, that we want to reduce. That is most important terms. That difference between these two we are trying to find out, these two, xt t plus 1, xt t plus 1. So these two, xt t plus 1 and p theta is t plus 1. This. So this for now as Gaussian we can say q of xt given x0. So in this format, because this is a Gaussian format where this alpha t bar is this multiplicative terms. So by definition of q of xt given xt and base rule, we can figure out that this q of t xt minus 1 given xt 0 is as this distribution. Now let this p of t of et1 is this particular distribution, where this mu theta xt is parameterized by a neural net. Minimizing LT means fitting this mu theta xt to mu tilde xt 0 using the gradient descent. So this is why we are trying to model our parametric model. We are set up our parametric model. Okay. Now this forward diffusion denoising process, from the forward diffusion can say is alpha t1 minus beta of t. If we let this and alpha t bar is that what we have said before. This xt, now what we are basically trying to do, we are trying to find out this relation between xt and xt minus. So this root over alpha t and xt minus 1 plus 1 minus alpha t, this, where this eating this epsilon t minus 1 epsilon, so these are the Gaussian wise. Now if we go for every steps, that it is keep on adding, and ultimately it is come up when on xt and x0, xt and xt minus 1, now xt x0 root over for t bar t x0, and this is very important. So if we get this, then we can say right that q of x0 is equal to this of this noise or this Gaussian distribution. So usually we can afford a larger update step when the sample get noisier. So beta 1 less than beta 2. So and therefore this alpha 1. So this is the basic understanding. This is the just mathematical understandings. We have to understand how actually we find out the relation between x and xt minus 1. Now, how we parameterize the noise. So noise parameterization refers to how the neural network in diffusion model predicts the reverse transition. Okay, that's the backward transition. Instead of directly predicting the denoise sample, the model predicts the noise added during the forward diffusion process. Okay, the forward process at Gaussian noise gradually that we are knowing. So forward diffusion equation is basically, as we see lot of time, there's this a q xt given xt minus 1 is this Gaussian distribution or Gaussian noise. Using the closed form of the diffusion process, what we have seen that xt is equal to this term that we have seen. But x0 is original data, this epsilon is Gaussian noise, and this alpha of t is basically the multiplicative, this 1 minus beta terms. So each noisy sample is a linear combination of clean data and noise. That we can understand from this. Now with this background, what we can do in reverse process, we want to learn p theta xt minus 1 given xt. So instead of predicting xt minus 1 directly, the model predicts the noise that this now, since this is a prediction, this is a parametric, so this is a noise parameter theta xt comma t. So forward equation from this forward equation is this. So this forward equation, this xt is equal to root over this alpha t x0 plus, because from start with x0 we get xt. So we can write this x0. Now it is had because we are reconstructing that, we just rewrite this equation xt minus alpha bar t with theta 0 xt t and root over, because now we write e theta 0 t because of this. This is our parametric. This allows the model to estimate the original clean sample, because this is the 0, this is the clean sample if we can model it. So this thing is called the noise parameterization. Now let's see how we can do it. Now what we can do, we know that the q of xt minus 1 xt comma x0 is this distribution, this Gaussian distribution, and this Gaussian noise. And now this mu t tilde is mu of xt x0. So we can write this mu t tilde is because of this 0 is this 1 by root over alpha t xt minus 1 minus alpha t root over, that we can write from this last slide, where this epsilon t is the noise added to the x0 to obtain xt. That we have seen, that this epsilon t is basically going to add to get xt, that x. So that is we have written here. So the model can be set as this mu theta 0 xt 1 by root over xt minus this term e theta 0 xt. Now because this is e theta, why? This is our model parameter, that noise model, where e theta 0 is the noise of the model of the noise, this epsilon t. Thus we can write this, that this xt minus this is coming from this xt minus this and this variance. So with this parameterization, minimizing LT means predicting and removing the noise, this epsilon t from a code update xt. So that we can understand that noise, this epsilon t is a noise, and that if we remove this noise, we can, from a corrupted xt, we can get back x0 or the previous version. So this is the mathematical formulation of noise parameterization. Okay, so how we can learn this noise? That this LT, that E of x, this expectation of x0, and this epsilon, C1 is a constant term. So this the norm, L2 norm in mu t xt or xt, mu theta, that square, and this basically C2 is equal to this. This we can write it. So ultimately we can say that this expectation of x0 is C2 into this norm, because we can put it the value of this E theta xt here. So we can put this. Okay. So we can get this LT, this parameter, this loss become now this. Now what is the, so if we summary all this small parameterization, learning, sampling, so we, these two very important result, that is written here, that we have discussed, and our training algorithm that we taken from this weight this, that repeat until converge. X0 is taken from the Q of x0, this distribution, then T uniformly, that is distribution. The sigma is the Gaussian noise. Take the gradient descent step on this because of these values, that how E minus this term. So that is the gradient step up. If we do this gradient, we can get this until converged. This is the training. And what is the sampling? The sampling is xt is basically n of 0. Now this is the noisiest version. For it is equal to the to reversing. So t of 1 to t to 1, and z, this is the Gaussian noise. Integrated then null is equal to 0. And xt is how the previous level, how are coming from this the later level. So xt, this xt, and this is the noise injection, and for this we return x0, and that in that way we can get back our x0 from this is the kind of sampling process. Basically you can say the reverse process. Okay, so this is the basic. So in summary, what we have discussed in this lecture, although bit mathematical, still we try to understand reverse diffusion and learning diffusion models via variation and inference, evidence in word bound is ELBO, loss, model parameterization, noise parameterization, and ultimately we conclude with algorithms of training. In the next class, we start autoregressive models. Thank you very much.